Hello, my name is Dr. Jonathan Butsky. I'm not a medical doctor. Instead, I'm the robot doctor. Robots need to be able to sense their surroundings, and a common way of them doing that is with eyes made out of cameras. Cameras are handy sensors for a robot because it allows them to see the same sorts of things that people see. For example, a self-driving car can use cameras to see stop signs and lane lines. A robot receptionist can see and identify people. And a small mobile robot can see obstacles and avoid them. In this lesson, we'll talk about vision, how robots see things, and how they can extract information such as distance from a set of images. And we'll do all of this using the math you already know: geometry, trigonometry, algebra, and a few concepts from physics. Today we'll explore points in 3 dimensions, so be ready with your pencil as we get started. Cameras are a very popular option for robots because of their similarity to human eyes, their relatively low cost, and the abundance of algorithms for extracting information from pictures. One such algorithm is the stereo vision algorithm. This algorithm allows the robot, using 2 cameras, to calculate the distance to nearby objects. For example, our robot can use stereo imagery to avoid running into a tree as it drives around. To explore this aspect of robot vision, we will follow 3 steps. Step 1, take a picture. This step produces an image, a 2-dimensional representation of the real world. Step 2, process the image. Find interesting points, such as corners and edges of objects in the image. We'll call these interesting points features. Step 3, calculate information. Use the features to extract information about the scene, such as where objects are, or the distance to particular features, or which objects are in view. Hey robot, you see that tree? To better understand robot vision, let's compare robot cameras to your eyes.
In order to see an object in front of you, light from a light source bounces off the object, goes through the lens in your eye, and forms an image on your retina. A robot's camera eye works the same way. Light bounces off an object, goes through the camera's lens, and forms an image on the sensor. The camera sensor itself is fairly small. Usually these sensors are measured in millimeters and are about the size of a fingernail, but can be slightly bigger or much smaller. The sensor is made up of a grid of very small individual color sensors similar to the cone cells in your eyes. These small sensors are known as pixels, a term you've probably heard before. Each pixel measures the color of one tiny point in the image. When you put all the small points of color together, you get the full image. The number of these small sensors, or pixels, determines the resolution of the camera. And for a typical camera, there can be millions of pixels.
Besides the resolution and sensor size, the other critical dimension of a camera is how far the image sensor is from the lens of the camera. This distance is called the focal length of the camera. We can use the focal length information later to help us determine an object's location. Now, let's look at an example to see how we accomplish our first step, taking a picture. We have our camera and an object, in this case a tree. If we look inside the camera, we can see the sensor and the lens. Imagine the lens as a simple pinhole. And we can see that the image is formed on the sensor at the focal length from the pinhole. We can also think of the pinhole as the camera center. This model of camera is called the pinhole model. We can also see why the tree is upside down on the sensor, since the pinhole takes a ray from the top part of the tree and focuses it on the lower part of the sensor, and vice versa. Dealing with an upside down image isn't very convenient. So what if we were to imagine an image in front of the pinhole at the distance equal to the focal length, instead of behind the hole? Since the rays from the tree would now pass through the image plane before they went through the pinhole, you would get a right side up image. We call this new image the image plane, and it's almost always used instead of the actual image on the sensor when describing what the robot sees. Now that we have our image of the tree, we need to figure out what to do with it. The next step is the image processing step. This step takes a raw image and finds interesting parts. We can find edges or corners of objects, for example. For our example of trying to avoid hitting the tree, we need to find the tree in both images. To do this, we look in both images for some common features of a tree. Features can be anything that the camera system can easily identify, such as unique patterns or corners. The key idea is that both cameras need to be able to see and identify the features, and they need to be unique. The intersection point of some bricks in a brick wall might be easy to find, but it isn't unique, so you can't tell which junction you are looking at. The final step is to analyze the images. That is, to calculate information from the features we've identified during the processing stage. One bit of information that the robot often wants to know is, how far away are the things I can see from me?
For our tree avoidance example, we want to be able to use these features to determine how far away the tree is so we can turn early enough to avoid a collision. One way of doing this is by using a stereo camera setup. Just like stereo sound produces different sound signals for your right and left ears, stereo cameras collect two simultaneous images with a right and left camera. The stereo cameras are arranged parallel to each other and are a known distance apart. From the simultaneous images they collect, we can calculate where the tree is relative to the cameras.
Let's start by looking at our setup from overhead. We have our tree in front of the robot and two cameras on the robot mounted 50 centimeters apart. If there is a feature on the tree at a point P, then it will appear on the image plane on the left camera at point A and at point B for the right camera. We also know the camera characteristics: focal length, sensor size, and sensor resolution. So how can we determine the distance to the tree from this information? Let's start by looking at the left camera up close. What we want to know is which way the orange ray is pointing. We want the equation for that line. Let's set the left camera center to be at 0, 0, 0. We know the camera characteristics. In this case, the focal length is 50 millimeters, the sensor is 10 millimeters wide, and is also 4,000 pixels wide. We know that the image plane is the XY plane, so the Z-axis is perpendicular to that and points out in the same direction the camera is pointing. We also know where our point P shows up in our image. That is, we know the X-coordinate for point A on the image plane. We know that the Z-axis goes through the middle of the image plane at point C, so the X-coordinate of C is 0. We also know that since C is in the middle of the sensor, it is 2,000 pixels from the right and left edge of the sensor. Let's say the feature we are looking at is at a pixel 2800, meaning it is 800 pixels to the right of center. Since the sensor is 10 millimeters wide, it is 5 millimeters from the center to the edge, and also 2,000 pixels from the center to the edge. Taking our pixel coordinate for point A, we multiply by our ratio of 5 millimeters per 2,000 pixels and get an X position of 2 millimeters. Now we know the location of the point on the image plane corresponding with our feature. X equals 2 millimeters and Z equals 50 millimeters. We also know that the line must go through the camera's center. X equals 0 and Z equals 0. From this, we can create the equation for a line through 2 points. Z minus Z1 equals Z2 minus Z1 divided by X2 minus X1 multiplied by X minus X1. We already know some elements of this equation. We will set point 2 to be the feature on the image plane at point A, which is located at the focal length along the Z-axis, and at the X-coordinate we have already found. We also know that the point 1 is the left camera center and is at 0, 0. We can simplify, and substituting in our values, we see that we get Z equals 25x. We can do the same thing for the right camera. In this case, the camera center isn't at 0, 0, 0 anymore, since the camera is mounted in a different position. For our example, the cameras are mounted 50 centimeters apart, so the camera center is at x equals 500 millimeters, and z equals 0. Just as for the left camera, we will start with finding the distance from the sensor center to the point B. In this case, the feature is centered at an x-coordinate of 800 pixels, or 1,200 pixels to the left of center. Multiplying negative 1,200 by our ratio of 5 millimeters per 2,000 pixels, we get an x position of negative 3 millimeters. However, remember that the origin is centered at the left camera center, so the true x position is 500 millimeters to the right, or at 497 millimeters. Now we have our 2 points and can find our ray through point B. Starting with our equation for a line through 2 points, we know that the second point is the B coordinate and has a z value equal to the focal length, and point 1 is at 500, 0. We substitute in the values and simplify, and we get our final equation. Z equals 8,333 1/3 millimeters minus 16 2/3 times x. Now we have 2 equations with 2 unknowns, x and z, the actual position of our point P in the real world. We can solve this system of equations by substitution, since they have z terms with a coefficient of 1. We can then rearrange the equation to solve for x, and we get a value of 200 millimeters for x. Now, substitute that back into either equation to find the z value. In this case, we'll use the equation for the left camera. And we find that the z coordinate is 5,000 millimeters, or 5 meters, which is about 16 feet. And that is our answer. The tree is at 5 meters in front of our robot. With these skills, the robot can now put its vision system to good use, identifying the objects around it, interpreting signs in the environment, and avoiding obstacles, all with a single type of sensor. Now, get your pencils ready for this week's challenge questions. A robot with a stereo camera pair mounted 30 centimeters apart with a 50 millimeter focal length and a sensor that is 16 millimeters wide with 4,000 horizontal pixels. Question 1 is, if a feature on an object is located at an x-coordinate of 3,000 on the left camera and at an x-coordinate of 1,000 on the right camera, how far in front of the robot is the object? Again, that is 3,000 on the left camera and 1,000 on the right camera. Where is the object? Question 2 is, why does the accuracy of this method become worse as the objects move farther away? It may help to think about what the distance is if the objects are 1 pixel from the center versus 2 pixels from the center. I'm John the Robot Doctor. See you next time.
You can find these video lessons at wqed.org/therobotdoctor.
Hey robot, what are you doing?